In this video, we're going to discuss a really important calculus concept of critical points. All right, so previously we learned about local extrema, which are the peaks and valleys of a function. All right, so we have our local maxes and our local mins. All right, so if we look at the local extrema in this graph, what do they have in common in terms of what we learned in calculus so far? Well, we have our two maxes and our two mins. And what have we learned so far in terms of calculus? We've learned limits and derivatives. If you look at the limits of these, they're not the same. All right, the limits of the green points are 5 and 7. The red points are 1 and 3. So their limits aren't equal. Well, the only other thing we learned is derivative, all right, which is the slope of the tangent line. So let's look at what the tangent lines are going to look like. All right, as I come up and look at what's happening for this graph, all right, as I reach the top of this valley, my graph kind of levels off for a second before it goes back down. So my tangent line is this flat line. At the bottom of this valley, again, these tangent lines are kind of having to turn to go back up. So how do you turn from going down to back up? You have to be flat for a second. Green point for the exact same reason. I'm turning from up to down. When that turn happens, I kind of have a flat bit to make that change. And same thing here. All right, so you can see all the local extreme in this graph have a horizontal tangent. And what do we mean about horizontal lines? Their slope is 0. So our derivative is the slope of the tangent line, has to be 0. So at every single one of these local extrema, the derivative is equal to 0. All right, so that's kind of one thing that they might have in common. All right, what about this example? All right, we have, again, a local max there and a local min there. But what do these have in common in terms of the derivative? Well, I kind of covered it up with the dots, but both of these have a sharp corner, a cusp. And we know at a cusp, the derivative does not exist. All right, so in the previous example, they all had horizontal tangents. In this example, the derivative does not exist. And these are actually the only kind of two possibilities that can happen at our local extrema. All right, so local extrema have a horizontal tangent line or no tangent line. All right, so that just means the derivative does not exist. All right, so the places that are going to be important for us are the places where the derivative is 0. That just means I have a horizontal tangent, or the derivative does not exist. All right, so these are the important points. So we're going to give them a name. And they're important, so they're actually like critical to our success in calculus. All right, so we're going to call these critical points. And there's two different ways you can be a critical point. You can have your derivative be equal to 0, which is kind of the most common one we'll end up using. But also when your derivative does not exist, that can also be a critical point for the same reason that those cusps are local maxes and mins, but the derivative does not exist. And why are critical points important? Because they're the places where local extrema can happen. All right, you either have a flat tangent at the top of a peak or the low of a valley, or you have this cusp that you have a peak there as well. So these are the places that local extrema can happen. All right, so we're going to find the critical points for a function. We just have to remember the definition. The definition of a critical point is we find the derivative, set it equal to 0, or we set the derivative, or figure out why the derivative does not exist. So both of these definitions, or both sides of the definition, use the same thing, which is the derivative. So my first step is to find the derivative. All right, using my power rule, x squared becomes 2x, minus 8x becomes minus 8, plus 3 becomes 0. So our derivative is just 2x minus 8. All right, this is just a line, so the line is never not going to exist. We don't have to worry about that side. We just have to figure out when does it equal 0. And we just solve this equation, and we get x equals 4. So we have one critical point for this function. It's when x equals 4. And then we'll talk about more about what we can do with this in class. All right, so find the critical points for this function. All right, we want to find, again, g prime of x first, because we're going to need it for those two sides of the definition. Find the derivative of this. You see there's this big division bar. All right, so we have to do the quotient rule. So don't forget our derivative rules now that we're trying to use derivatives for stuff. All right, so we're going to have low d high minus high d low all over low low. And so we're going to be applying this to something, to a definition. We want to try to simplify a bit. It's going to be x minus x plus 3 over x squared, which is 3 over x squared. All right, so now we have to do two things. We have our derivative. We have to figure out first, when does this equal 0? All right, so this equals 0. 3 over x squared equals 0. I got to multiply both sides by x squared to get rid of that fraction. 3 equals 0. And that's not possible. So my derivative never equals 0. All right, so there's no critical points on that side of the definition. But don't forget the second part. All right, we use this left-hand or first part of the definition so often people forget about the other part is when does my derivative not exist? And whenever we're working with something with a fraction, it doesn't exist when the denominator is equal to 0. Because you can't divide by 0, it wouldn't exist. Take the square roots, we get x equals 0. All right, so in this case, we only have one critical point, and that's at x equals 0. All right, so here's one for you to try on your own. Find the critical points of this function. All right, pause the video, try it yourself, and I'll show you the answer in 3, 2, 1. And you get 2 critical points for this function. You take the derivative, you get this quadratic. You set it equal to 0. You have to practice your factoring, and you get these 2 critical points. And again, there's the second half of the definition when h prime of x does not exist. But the derivative we got is a polynomial. We just have coefficients and powers of x. Everything works out nicely. It's never going to be a time where our derivative doesn't exist, so we just have these 2 critical points. So keep in mind for now that critical points are just a possible local extrema. So that second example we had, the g of x, which was a fraction, that critical point we got was actually not a local extrema. So we'll figure out ways to check this as once we find the critical points. I will discuss that in class, but for now, just knowing what a critical point is and being able to find them is the first step to doing that. All right, so local extrema happen when the derivative is 0 or undefined, and we call those critical points. All right, so the x values where those 2 things happen, where the possible local extrema happen, are our critical points.